Good day, guys. Today we are going to do the Zener diode input voltage regulation. In this example, I'm going to illustrate to you that for as long as your Zener diode maintains a certain amount of current across it. So this is the graph of a Zener diode. And over here I have IZK. And over there I have IZM. So for as long as operation is maintained within those boundaries, the output voltage, as you can see, remains almost constant. So I'm going to use an example to illustrate that by calculating the minimum input voltage. In our next lesson, we'll do the maximum input voltage. So in our example, we have this circuit here, which I'm going to draw now. Okay, and then our R here is 100 ohms, and then we have the variable input voltage. Let me remove this part here. Okay, so our Zener is specified as this one here, 1N4733A. Okay, so according to the specification here, for this Zener, we have Z as 7 ohms, IZT is given as 49 milliamperes, and IZK is specified at 1 milliamperes. Okay. So to do our calculations, we start by calculating V out, because V in is VR plus VZ, which is our V out. And if I'm calculating V in minimum, then VR, as I break it down, is going to be IZK times R plus VZ, which is my V out, is VZT plus ZZ multiplied by IZK minus IZT. Okay, so in this case, IZK is 1 milliampere times R is 100 ohms plus VZT is given as 5,1 volts plus 7 ohms into 1 milliamperes minus 49 milliamperes. Alright, so this, after calculation, you'll see it gives us a value of 4,76 volts. This is my V out. Let me just do that. Here we have 1 milliamp times that, which is 100 millivolts plus the output voltage here, which is VZ. And our output voltage here is 4,76 volts. So your input minimum voltage will be 4,86 volts. This is the input voltage, the minimum input voltage. Now, if we go a step further and calculate the V in maximum, let's get another page. V in maximum will be given by the formula IZM multiplied by R. So this is the voltage across R plus your V out voltage, which we've given as VZT plus VZZ. So in this case, first, to get IZM, as it's not specified in the datasheet, will be IZM is given by Pdmax divided by VZT. So Pdmax in this case is 1 watt for all the temperatures of up to 50 degrees Celsius. If it's not 50 degrees, anything above that, then we have to calculate it. So in this case, nothing was specified about the temperature of the Pdmax, so we use 1 watt. And by calculation, this gives us 196 milliamperes. Now we take this and put it into our formula then. Therefore, V in maximum would be IZM 196 milliamperes times the value of R 100 ohms plus V out VZT, which is 5,1 volts, plus ZZ 7 ohms into 196 minus 49 milliamperes. The final answer that we have for our V out from this calculation is 25,7 volts. So if we analyze this, we'll see that V in maximum, when IZ was at maximum, which is IZM, we had 25 volts. And when V in minimum was calculated at IZK, our input was 4,86. So there is a variation here of your input from 25 to 4,86, whereas your output was only 4,76 to 6,13. The voltage here is 6,13 volts. So it shows that for as long as this variation is maintained, your Zener will be able to stay within the constraints of your regulation. Here we have IZK and here we have IZM. So for as long as current on the output goes between IZK and IZM, the voltage, which is represented by this part here, the voltage will be as constant as possible, because this is what the Zener does. When the current flows in through it is IZ. Let me just show you that. When the current flowing through it is, so this is our typical circuit. IZ, and that is IT. So the current flowing through my Zener from this graph IZK, IZM. Now for as long as we have this current within these boundaries here, the current flowing here not less than IZK or not more than IZN. Then the voltage that we are going to measure here will always be a constant voltage. Even if when my input is variable, the output voltage will always be constant. And that is our lesson for today. Thank you very much.